Okay, so let's take a look at a particular problem. If P dot Q is equal to P dot R, and this is for some non-zero vector P, then does this mean that Q is equal to R? If P dot Q is equal to P dot R, then does this mean that the vectors Q and R must be the same? Well, let's take a look at this and rearrange this first. We have P dot Q minus P dot R, and this is equal to 0, right? And from this, since we know that the dot product is distributive, we've shown that the dot product is distributive, we can factor out the P, right? And this will become P dot Q minus R, and this is equal to 0, right? Now from this, can we conclude that this vector and this vector must be the same? Well, not necessarily. The most we can say from this is that the vector P and the vector Q minus R, right? So this vector that we get, these two vectors must be orthogonal, right? They must be orthogonal, meaning they are perpendicular to each other. Since the dot product of these two vectors is equal to 0, right? We cannot really say that Q is equal to R just yet, right? So what we can do is we can look for some vector that if I find the dot product of P with that vector, I will get 0. So let's say that P is equal to 2 minus 1, for example, right? So from this, we can find some value of x and y so that the dot product of 2 minus 1 of this vector with some column vector x, y gives us 0, right? So what can be our x and y values so that these two vectors is equal to 0? Well, we can consider our column vector xy to be equal to 1, 2, right? If that is the case, then 2 minus 1 dot 1, 2 will be 2 times 1 plus minus 1 times 2, which gives us 0, right? So we know that P dot Q minus R is equal to 0. And since this is P, we can say that this is Q minus R, right? So we can say that Q minus R is equal to this column vector 1 and 2, right? And if that is the case, then P dot Q will be equal to P dot R, right? So from this, what we can do is we can actually choose any column vector for R. We can have our R vector to be any column vector, and by substituting that column vector, we can find our corresponding Q, right? Because at the end of the day, if I choose any R and find the corresponding Q, Q minus R will be this column vector anyways, and the dot product of P with this column vector will be 0. So this will be satisfied, right? So let's say that arbitrarily we are choosing R to be this column vector 3 and 2, right? If that is the case, then I will have Q. So from this, I can have Q to be equal to this column vector 1, 2 plus R, which is 1, 2 plus the column vector 3 and 2, right? And if I add these together, I will have 4 and 4, right? My x and y components will be 4. So R is this column vector and Q is this column vector, right? And once again, Q minus R. So 4, 4 minus 3, 2. As you can see, this just gives me 1 by 2, which is Q minus R, right? And the dot product of this with P will be 0. So you can see that this satisfies this equation here, right? So since I have my Q and R, I can see that P dot R is equal to P dot Q. So let me write this the other way around. P dot Q is equal to P dot R. We know that P is what? P is 2 minus 1. I have Q, which is 4 and 4, and this is equal to 2 minus 1 dot 3, 2, right? So as you can see on the left hand side, we have 2 times 4 plus minus 1 times 4, right? And on the right hand side, we have 2 times 3 plus minus 1 times 2. So we get 8 minus 4. So we have 4, and this is equal to 6 minus 2, which is also 4. So you can see that the left hand side and the right hand side are equal. So this is satisfied, but yet the vectors q and r, they are not equal, right? We have two different vectors, q and r, they are not the same, right? So if p dot q is equal to p dot r, this does not necessarily mean that q and r are going to be the same vectors. It is possible for them to be the same vectors, but that does not mean that they will be the same vectors every time, right? We cannot just assume these two will be the same. So in general, if I have the dot product of u and v to be equal to u dot w, we cannot assume that v and w are equal, right? We cannot say that these are necessarily equal, right? So let's take a look at a different problem. So let's say that we have an inequality like this. We have x1 y1 plus x2 y2, and this is less than, so the square of this is less than or equal to x1 squared plus x2 squared times y1 squared plus y2 squared, right? So we have this inequality and we have to use the dot product. Let's try and use the dot product to prove this inequality, right? So how can we do this? If I take a look at the left-hand side, if I take a look at this term, if I ignore the square, what does this look like? This just looks like the dot product of two vectors, right? So for my left-hand side, let's say I have a vector x, and this has the components x1 and x2, and I have another vector y with the components y1 and y2, right? So if I take the dot product of these two vectors, I will get x1 y1 plus x2 y2, right? As you can see, this is the same as what we have here, right? And if I take a look at the right hand side, if I find the magnitude of x, so the magnitude of x, this is just equal to the square root of x1 squared plus x2 squared, right? So this portion looks like just the square of my magnitude, right? This looks like, so this just looks like my magnitude of x squared, and similarly this looks like the magnitude of y squared, right? So the product of the magnitude squared of x and y, this will just be equal to x1 squared plus x2 squared times y1 squared plus y2 squared, right? And this is just what we have on the right hand side here, right? And we also know, we've also shown that the dot product of these two vectors can also be written as the magnitude of x times the magnitude of y times the cosine of theta, where theta, this is the angle between these two vectors, right? And we can rearrange this for cosine of theta, which will be x dot y divided by the magnitudes of x and y, right? So now, what is the maximum and minimum value of cosine that we can have? So for this cosine function, we know that the maximum value will be 1 and the minimum value that it can have is minus 1, right? So the magnitude of cosine of theta has to be less than or equal to 1, right? Since we're taking the magnitude, the negative values will become positive. So the magnitude of cosine theta will be less than or equal to 1, right? So from this, if I take the magnitude on both sides, I will have, so the magnitude of x dot y divided by the magnitudes of x and y. This is equal to the magnitude of cosine theta, which is less than or equal to 1, right? Now we know that this must be non-negative. This portion is also non-negative, and this is due to the magnitude, due to the absolute value. So we can just take the square on both sides, and doing so, we will have what? So first of all, we have x dot y, which is x1 y1 plus x2 y2, and since we're squaring both sides, we will have this squared in the numerator divided by the magnitudes squared, right? And we know that this will be x1 squared plus x2 squared, right? This is the magnitude of x squared times y1 squared plus y2 squared, and this is the magnitude of y squared, right? And this is equal to cosine of theta squared, and this must be less than or equal to 1 squared, which is just 1, right? And from this, if I multiply both sides by my denominator here, I will have x1 y1 plus x2 y2 whole squared less than or equal to 1 times my denominator, which is x1 squared plus x2 squared times y1 squared plus y2 squared, right? So what we have done is we have just proven the inequality that we were given using the dot product of two vectors. When does the equality hold for this? So when is my left hand side and the right hand side equal? This is equal when cosine of theta must be equal to 1, when the magnitude of cosine of theta is equal to 1. And when is this equal to 1? This is equal to 1 when theta is either 0 degrees or theta is equal to 180 degrees, right? For these angles, cosine will be equal to 1. So this equality, so x1 y1 plus x2 y2 squared, this is equal to x1 squared plus x2 squared times y1 squared plus y2 squared, right? This happens when theta is equal to 0 degrees and theta is equal to 180 degrees. So when theta is equal to 0 degrees, this means that my vectors x and y, they are parallel, right? They are both in the same direction, and the angle between them will obviously be 0 degrees, right? And when theta is equal to 180 degrees, then in this case, my vectors x and y are actually in completely opposite directions. So they're still parallel, but they're in opposite directions. Whereas for 0 degrees, they are in the same direction, right? If my vectors are in opposite directions, then the angle between them will be 180 degrees. Right, since my x and y vectors are parallel, they can have the same or different magnitudes. It is possible for my x and y to have the same magnitude, or they may also have the different magnitude, although they are parallel. So we can write the vector x to be equal to y multiplied by some scalar quantity, right? And c here is non-zero, right? And the equality will hold. The equality will hold if x is equal to c y for some non-zero constant c. If x is equal to cy for some non-zero constant c, then theta will be equal to 0 degrees or theta will be equal to 180 degrees, right? And in this case, the magnitude of cosine of theta will be equal to 1. And the equality, so our equality, it holds for these cases, right? So the inequality that we have just proven, this inequality here, this is our Cauchy-Schwarz inequality. This is known as the Cauchy-Schwarz inequality.